Our last topic in this section is the topic of differentials. Now, differentials are abbreviated with dx, dy, dz. We've seen them for a long time, since Calc 1. And if you remember, what they stand for is an infinitesimally small change in the particular variable, right? So delta is the symbol we use for subtraction, for the actual change. And then as we let that actual change get smaller and smaller, the difference gets smaller and smaller, it becomes a differential. It was a limit argument we made in Calc 1. Okay, so delta z is the actual change in z. So you have two z values, one at the point of tangency and one somewhere close by. And the actual change in the z values is delta z, right? So that would be, if this is some function, it would be f of, actually, let me do it in the same color. F of x plus delta x, how your x changed. Oh, x plus delta x, comma, y plus delta y, because this is a function in two variables. Of course, in Calc 1, it would only be x plus delta x. And then we didn't have the y plus delta y added in, but now we're going to add in this second piece. That's what makes it Calc 3. All right, so this is that actual change, right, from the point of tangency to that point right there. So what was the actual y change? And so what we can use is the differential. So the differential is not on the green surface. So these two dots are on that green surface. But instead we can use the point of tangency on the green surface and a point nearby on the tangent plane instead. And that will give us the differential. So that is dz equals the derivative with respect to x times the dx differential plus the derivative with respect to y times the dy differential. So this is dz right here. And this is delta z right here. So delta z is the actual change. And then, if you will, this is sort of an approximate change. You'd be using the tangent plane. And what's happening is you're using the derivative with respect to x. So it's like you're cutting across it with respect to x. And then you're saying, okay, with respect to x, this is how the derivative is. This is how the slope is. And I'm just going to multiply by my change in x, right? So that'll kind of make it climb in one direction. And then you do the same thing with the derivative with respect to y, which gives you, if you're cutting across it at the y, with a y plane, and then the derivative, or that differential with respect to y, that small difference in y. So it's like you're climbing over and up in two different directions to get that vertical lift that you're looking for, the change in z. Okay, so now let's use this in an example. So given the function z equals the square root of x squared plus y squared, which for the record we all know is x squared plus y squared to the 1/2 power. Just thinking ahead because we're going to have to use different derivatives here, differentials here to do this. So we want to use the method of differentials to approximate the change in z. See, so this gives us an approximate change. When moving from the point 3.4 to the point 3.06, 4.1. Compare your results, blah, blah, blah. Okay, so if we look at, and we want to compare our results, so we actually want the change in x and the change in y as well. So we have a whole bunch of things that we need to figure out. So the first thing we need to figure out is our dx, right? How did our x change? So dx, which is delta x, is from 3.06, take away 3. So our dx is 0.06, or delta x, same thing. dy, well, they're not the same, but they are the same for our purposes with this particular formula. Delta y, dy is the limit of delta y as your number of values increases. So in Riemann sum examples, it was the number of rectangles, and that's of course going to change for us because we're three-dimensional, but it's that idea. Okay, so we know our delta x and our delta y. There we have it. Okay, so now we could find the actual value right away, or we can find the differential. It doesn't really make any difference. So let's find the actual delta z. Oh, Actually, I take it back. It wants us to use the method of differentials first, so let's do that first, and then we'll compare later. Okay, so to find the differential, we're going to need f sub x and f sub y, right? We already know the dx and dy. That's 0.06 and that's 0.1, so that's relatively easy. But we need that fx and fy, so let's find the differential. So f sub x is, wrong color. There we go. Okay, so f sub x is the derivative of this with respect to x. So we would bring the 1/2 down, x squared plus y squared to the negative 1/2 times the derivative of the interior, 2x. We've seen this in previous problems. This is x over the square root of x squared plus y squared. And then fy will be the same thing, except it'll be 2y in the back. So it'll be y over the square root of x squared plus y squared. All right, now this is all well and good, but it's not really going to help us with our, well, I mean, it is going to help us, but it's not what we need for our particular problem. So we don't multiply these values with variables times that. So what we need to do is substitute in the values we had, the value we're coming from, which is 0.34. So we're going to take the 0.34. So these are the derivatives everywhere. So derivatives everywhere at all points. And we need to find the derivatives at our particular point. So f sub x at 3, 4, because we're using 3, 4. 3, 4 is the point of tangency, right? That's the point we're coming from. And we're going to move to this one that's just really close by. So 3, 4 would be 3 over the square root of 3 squared plus 4 squared, and we've run into this before. That's 25. Square root of 25 is 5. So this is 3/5. And f sub y at 3, 4 would be equal to 4 over the square root of 3 squared plus 4 squared, which is 4 over 5. All right, so these are our particular values. Right. All right, so now we can put it together. So now the differential dz is equal to 3/5 times the change with respect to x. So it's fx dx. Actually, let me rewrite the formula just real quick. That way you have it down here as well. So it's fx dx plus fy dy. That would be equal to 3/5 times dx, which we found to be 0.06, plus 4/5 times 0.1. 0.1 goes in here, 4/5 goes here. And then, of course, we just make a computer do that, and it will come up with 0.116. I can show you in Maple because I did it. There it is. I even had it verify my derivatives for me for fun. Interestingly enough, Maple, without the simplify command, gave me 3 square root of 25 over 5, which the square root of 25 is 5, so I don't know what, or over 25. So I don't know what it was doing there. So I put a simplify command in front of it as well. And there we have it. So 3/5, 4/5, and then I put it in right there. Oh, and then there's the actual value if we want to see it. So, because we wanted to make that comparison. Okay, so this is 0.116. This is the approximation. Right. Okay, so then what's the actual change? The actual change in z is delta z, which is f of, well, it's in our case, it'd be, here, let me write it, x plus delta x, y plus delta y, minus f of xy. So in our case, that would be f of 3.06 comma 4.1, take away f of 3, 4. And of course, if you're wondering, well, if we can do this, then why didn't we do this from the start? You're learning a technique that allows us to basically get away without having to do difficult problems. So sometimes the z is just really hard to work with. And we can come up with a tangent plane, and that's easy to work with. So a lot of times it's easier to work with the plane because planes are so simple than it is to work with this really complicated curve. And if all we need is a few decimal places of accuracy, then we're good. And I made Maple do this. Um, so it's the square root of 3.06 squared plus 4.1 squared. That was the function, minus the square root of 3 squared plus 4 squared. And according to Maple, it was 0.116, 0.14, 0.3735. You can see it right there in my Maple. So there it is. Oh, I didn't have the 5 on there, but it is. All right, so there's that piece. So according to Maple, this is the actual value. And we're supposed to compare them. And you can see they're very close, right? They're very similar to each other. And also, they should be setting off a little bell in your head because we've seen these numbers before. If we look at the previous example with the linear approximation, the change in the two problems, right? This was 5.116 with all the zeros after it. That was using the approximate, whereas the actual had this piece in the back. Just scrolling back to the Maple on that one so you can see. So there was the actual value, there's the approximation. So the numbers are very similar, and so our approximation is very good, right? And this change is the same change we saw in the previous example. There, and I just wrote that up, right? The numbers were very close, so our approximation is good. And if you want to make a note to yourself, this is the same thing we were doing with the previous example with linear approximation. Well, it's not the same, but they're closely related.